Hello everyone. In this video we are going to talk about some basic yet very important relations that you need to know about images. So the first one is the size and distance for objects in an image. If you remember from perspective projection, the pixel coordinate of a point with XYZ coordinate in the word frame or the camera frame can be written as u and v, horizontal and vertical pixel coordinates, where u was 1 over z sxf times x plus u naught, and similarly v was 1 over z syf y plus v naught, where u naught and v naught were the coordinates of the center of the image, right? In the image plane or camera CCD basically, and f was the focal point, sx and sy were the number of pixels per millimeter of the sensor in horizontal and vertical directions, z was the depth, and the product of sxf and syf, we call them alpha and beta. So if you write this relation in terms of delta u and delta x, delta v and delta y, these are the results. Delta u is 1 over z alpha delta x, delta v is 1 over z beta delta y, where delta u and delta v are the length of the projection of the object in the image in terms of pixels in the horizontal and vertical direction, right? And delta x and delta y are the actual sizes of the object in the word frame. So here, for example, this distance from here to here is like the delta x maximum for this person, and this distance from here to here is like delta y. Whereas if you look at the image plane, this distance from here to here is like delta v, and this distance from here to here, this guy is delta u. So those delta u, v, x, and y are related through alpha and beta and through z. Now the question is this: if there is an object with a known size in the word frame, and I look at the picture of that object with the known size, and I can measure for that object, let's say a delta v or delta u or a combination of them, is there a chance I can estimate the depth or the range or the distance between the camera and that object? The answer is yes. You know, when you take pictures, z is always the piece of information that is lost, because you go from 3D world to 2D and the depth is lost. But can I retrieve the depth? Yes. As long as I know how big the object is in the word frame, let's say, for example, if I just look at the vertical direction, I know this delta y of the object, so I can measure this. Beta I can get from camera calibration, and delta v I can measure from the image. Okay, so if I want to write them, this one you measure in the image. This delta y is known, and this beta you get it from camera calibration. Can I retrieve the depth or the range? The answer is yes. All you need from this formula is to solve for z, which gives you this second formula. Z is equal to beta delta y over delta v. The other way around, if I know the range, if I know this distance from here to here, this one, this distance z, if I know this, right, and I measure this delta v from the image again, and I know beta from camera calibration, can I estimate the actual size of the object in the real world? Again, the answer is what? Yes. So you see, I can retrieve the actual size of the object or depth if I know the other piece of information. Let me show you an example which shows you the application for this. So here, I show you a picture I have taken with my webcam from a ruler, and 2 points on that ruler are 6 inches apart. Let's take a look here. So this is a ruler, and here between 0 to 6, there are 6 inches apart, those 2 black points. So I know exactly the distance between them, and the word is 6 inches. Now I use the IM tool command, so I can measure in the image the vertical distance, or delta V, between those 2 points. So if I go here and I zoom, here I click on this measuring tool, and then I click on the first black point and drag it to the second black point like this. And if you can see roughly here, the distance is about what? 278.97, or I can say 279 almost. It's like 279 what? Pixels is the distance between them. So now what I can do is say 278 or 279, let's say, correct? And now that I know del V, del Y, and here you see 6 inches, I converted it into millimeters. Alpha and beta, I found them from camera calibration. Please watch my previous video on MATLAB camera calibration app. And you see in that video, I use camera calibration with the picture of a chessboard, and I could find the intrinsic matrix K, and in that intrinsic matrix I had alpha and beta, these 2 numbers. This picture is taken with the same camera I calibrated. So this is the alpha and beta, and then here I use this beta here, and you see beta delta Y divided by delta V divided by 25.4 to convert it back into inches. This is the distance that I think I have taken the picture of that ruler from the camera. So if I calculate it, it gives me 17.67 inches. And when I used my ruler, I don't know if you can see something or not, but let me show you. Here, this yellow thing that you see, that is my ruler, measure tape. This is my measure tape, and I could roughly measure the vertical distance because this was laid on the flat floor. It was roughly the range, the distance between the ruler and my camera. When I measured it, it was roughly close to 18 inches, not exactly close to 18 inches. And look at this number. Look at that. It's very close also to what? To 18 inches. So you see, did I know my range? No, but because I knew that ruler was 6 inches, I could easily estimate my range to a very good approximation, right? The approximation here is just a few percentages, 1 or 2% or something like that, correct? So it is like 0.3 or so divided by 18. Yeah, it's less than 2% error. Also, on the other hand, if I use the other formula which I showed you, I know my depth, which is about 18 inches. What is the size? What is the real world size between those 2 black spots? If I do that one, look at this. It says it's 6.11 inches. And that is, the actual distance is almost 6 inches. So you see, I can measure my real world distance if I know the range at which I took the picture, right? If I didn't know it's between 0 to 6, using this, I could easily do the measurement. So these are 2 simple yet very effective and very important formulas. As long as you have some clue about one piece of info, you can estimate the other piece of information. The other things that might be useful about the cameras that I have not discussed so far are fields of view, the angles. Okay, these are some of the things that you see when they describe a camera. One of the things they describe is field of view, horizontal, vertical, or diagonal field of view. What are these? So if you look at here, this image plane, and which is at the focal distance from the pinhole location, this kind of what you can see, this pyramid, it has two angles, a horizontal opening angle and a vertical opening angle. And you can even define a diagonal one, where the relation between diagonal, horizontal, and vertical comes from a simple Pythagorean theorem. So here, if you consider the size of the camera CCD, the size of the sensor, to be h mils by w mils for horizontal and vertical directions, then the diagonal here, the diagonal of this sensor is going to be a square root of h squared plus w squared. So the ratio between h and that diagonal is going to be the same ratio between horizontal field of view and what? The diagonal field of view. Again, the diagonal is like an angle that corresponds to the diagonal opening. So it's an angle like this, basically. It's an angle like that. That opening angle you might call the diagonal, DFOV, as opposed to HFOV and BFOV, because this is what you typically see in when you buy a camera. They say the field of view of the camera is 60 degrees, right? So when they say this is 60 degrees, it doesn't mean horizontal or vertical. It's the diagonal. And you can use that to estimate what? Your horizontal one, using a simple Pythagorean theorem. Fine. Now, the question is, what does this HFOV, the horizontal field of view, or the vertical, have to do with the sensor size along that direction? So if it's horizontal, what does it have to do with H, the horizontal size of the sensor, and what? F, the focal length. Well, here, if you look at this pyramid, you can easily see a what? You can easily see a triangle. For example, if you look from the top, if you look at the top view, what would you see? You see a triangle like this, where this vertical where this perpendicular is F, and then each one of these two segments is H over 2, right? And each one of these angles is HFOV, horizontal field of view, divided by 2. Because the whole thing is the horizontal field of view. So now what is it? Clearly tangent of this HFOV, which is in degrees, divided by 2, whatever it is, tangent of that angle is equal to what? Equals to H over 2 divided by what? F. So what I need is to take arctangent from both sides, multiply by a 2, and that gives you this formula. That HFOV is 2 arctangent of H over 2 divided by F. Similarly, if you look from the side, this direction, you can see a triangle like this. This time, what you have is, again, this is F. Each one of these is W over 2. And each one of these angles is V FOV divided by 2. So what can I say here? I can say that tangent of VFOV divided by 2 is W over 2 divided by F. And similarly, that means, again, if you want VFOV, this is 2 tangent inverse of W over 2F. Which is very similar to this one. Just change this H to W, then this horizontal becomes vertical field of view. Correct? So that's how you can find it. So now let's say here from the manufacturer gave me the DFOV. This DFOV you can easily find on any manufacturer's website. They give you DFOV, say the angle of view of this camera is 60 degrees. Again, when they give that information, Most probably it's the diagonal, not horizontal or vertical. The other thing you can find on many manufacturers' website are H and W. They give you the sensor size. If they give you the sensor size, H, W, and VFOV, if you get these three pieces of info from the manufacturer, then you can find, let's say, HFOV yourself through this formula, plug it in here, and guess what? In this formula, once you know H and HFOV, you can find what? You can find F, the focal length. Because focal length is most of the time is not directly given to you, even by a manufacturer. They don't typically directly give you the focal length. For example, for this camera, myself, which is a, where is it? It is a Logitech HD webcam C270. That's the webcam I used. I looked all over the place, including the Logitech website themselves, and all I could find was that the angle of view of this is 55 degrees, and the sensor sizes on another website I could find 3.58 mil and 2.02 mil. So I could find these from the manufacturer, but I could never find what? The focal length. Can I find it myself now? Sure. You see, I found the HFOV through Pythagorean theorem, and I could also calculate VFOV if I was interested in, and then I found the focal length here. Once I have the focal length, if somebody says, what is this SX and SY that you had for your camera? If somebody asks for them, you can find them as well. Remember, you have the product from calibration, you have the whole product. You have this and this from calibration. This is alpha, this is beta. I could find the product of F with those SX and Y, but not F alone or SX or SY alone. So now that I have F and I have alpha and beta, guess what? I can find SX and SY by simply dividing alpha and beta by what? F, and this is exactly what you see I have done in this code. So here, if I run this code again and do the image measurement, which I did already with the IM tool, then guess what? It gives me the information. Hey, this is the range that you took the picture of. If I knew the range 18 inches, this was the distance between those two black points. Your horizontal field of view is about 47.9 degrees. Vertical is 27.02 degrees. Your focal length is about 4.03 mils, and your SX and SY are 202.9 and 203.9 pixels per millimeters. Okay, so because you need this to calculate these parameters for many calibrations, for many calculations and so on, I decided to publish this video and tell you how to do these calculations. The most interesting one, the most attractive formula out of all of this is this one for me, measuring depth, because that is the piece of information that you lose in a camera. The only important thing is this. Look, here I'm actually using 2 points, right? I have delta V and delta Y. As you saw in that image, I had 2 black points. The important thing is this. Since I factor out Z between these 2 points, what does it mean? It means this Z has to be what? Has to be constant for those 2 points. So you have to make sure that the 2 points that you took the picture from, they are at a constant Z. Like for example here, if you consider 1 point on the head of this person, and let's say 1 point on the foot, and you measure delta Y between them, or then in the picture you measure delta V, you need to make sure the Z, the distance of these 2 points to the pinhole location or to the camera, these 2 distances are the same. If they are different, if one of them is Z1, the other one is Z2, and those Z's are quite different, this formula I wrote for you is not applicable. Now, when is it that you can assume this is a good thing? One case is when this Z is what? Is large. When the distance from your camera to the object is very large and your object is not a very deep object like a big train or something, then you can roughly assume, as long as it's roughly a vertical object and it's not super deep, you can say almost, as long as these z's are big, I can say these two z's are what? Are basically relatively the same. Okay, so z1 and z2, you can say they are roughly the same. And now that I mentioned all of that, let me give you one bonus thing. Sometimes you might wonder, how far from an object can I see it in the camera? That's one of the things, the maximum range, correct? You might want to know, how far away from some object can I still see it in the camera? Can you get an estimation from this formula here? The answer is yes, you can. How would you do that? Well, clearly from this formula, any of them, whether this one or the combination of them, you clearly can see that the range does depend on the size of the object. It does depend on delta x or delta y, how big the object is, correct? Of course, the bigger the object, the bigger the range at which you can see the object, right? So it does depend on the size of the object. So if I know the size of my object, let's say I know this delta y, I know how big the object is, then at what range can I still see the object? Well, it depends on your threshold for seeing the object, but let's say that's the smallest you can go. How far you can go with, and you still say I can see the object? When that's where this guy is what? It's like 1 pixel. This guy has to always be bigger than or equal to 1 pixel, otherwise it's impossible for you to see it. Correct? If that is the case, like that delta V is like the minimum it could be, then from here you can find what? Z max. So Z max, the maximum range, is going to be what? It's simply going to be B delta Y divided by delta V min. And if this delta V min is 1, it is going to be simply beta times delta y, right, for vertical direction. In the horizontal direction, what? From horizontal formula, you can say, again, from here, that your Z max is going to be alpha times delta x. Correct? Because, again, you can say this guy is bigger than or equal 1 pixel. So now the question is, between this max range and this max range, which one would you choose to calculate the maximum range? And guess what? The answer is the minimum of them, because you have to be able to see the object as 1 pixel in both directions. So if I want to give you a formula here, let me write it down for you. And so here is what? Here is your Zmax formula. So I can add that portion to the code by measuring the maximum x and maximum y, let's say for that ruler. If I know the maximum x of that ruler and I know the maximum y of that ruler I just showed you, and I know alpha and beta, I can give you what? A maximum range. So for this ruler, the maximum delta y is a little bit over 6 inches, and your delta x is a little bit over 3/4 of an inch. So I measured them here, and your delta x is about 0.8 inches, and your delta y is 6 3/16 of an inch, which is 99/16. So here I multiplied alpha by delta x and beta by delta y, and then I get what? The minimum of the two, which if I run here, you see, this is in millimeters, 16.62 meters, right? Or 16,000 millimeters. So if I want it in meters, 16.62 meters. This is the maximum distance at which I can see both of the horizontal and vertical directions of this ruler at least as 1 pixel, right? So again, it depends on the size of the ruler. If it was a bigger ruler, definitely that maximum size would have been something bigger, but clearly for this size, up to 16 meters, 16.6 meters, I can barely see the ruler. Again, it's 1 pixel. Whether you can see an object with 1 pixel or not, you have to be very good at it. You have to zoom in. But again, if you count the minimum value del U and del V for detection, then you can count it as what? You can count it as your final number. If you don't think you can do it at 1 pixel, then what you can add is, I recommend you add a del U minimum here, right? And also a del V minimum for delta Y, just like this formula that you can see here. So hopefully this video was useful to you, and I will see you in my next video. Thank you so much.